Hello guys, welcome to my YouTube channel. And in this video, we are going to see about the gradient descent. So in my previous video, I have talked about the linear regression by utilizing the gradient descent. So there aren't only the parameter estimation techniques like gradient descent is available. There are also other estimation techniques like ordinary least squares and the neighborhood related algorithm stuffs. So among them, the most prevalent usage of the parameter estimation techniques comes from the gradient descent. And so I have utilized the gradient descent for the explanation of the linear regression. So in this video, we will be just seeing about how gradient descent works and what is actually in the internal working of gradient descent and along with the types of the gradient descent. So if time permits, I will also showcase you the code implementation of these gradient descents. So let's dive into the topic. And in gradient descent, before we move into the gradient descent, there are certain topics which we need to cover. So which they are like the cost function and then the gradient. Okay, so moving to the cost function, the cost function is actually the summation of all the errors of the individual training data. Say, for example, I have x and y. It is the actual value, and y hat is the predicted value. So y hat is 3 and the actual value is 2. So y hat minus y gives me 1, and 4 minus 3 gives me 1. So this value is actually called as the error function, since a single data point is considered, and the cost function is simply the summation of all the error functions. So it can also be demonstrated as the mean square error. Okay, so keeping it simple, the cost function can be explained with a simple formula of 1 by 2 into the total number of records in the data set, which is n, and then summation of I is equal to 1 till n, which is I'm iterating over the entire data set starting from this first data point till the last n, and then y hat minus y, the whole square. So I think you are all clear up to this point. So the next comes is the gradient. So now I have got the cost. Cost can also be demonstrated as j of, you can keep it simple as j of theta. Okay. So consider this as a graph which has weights as x-axis and cost in y-axis. Say for example, if my weight is 1, my cost is very high, which is around 20. So as my weight increases, my cost decreases. And here comes a graph like this structure. Our optimal aim, we have to reduce the cost to the global minimal. So this is the global minimal where the cost is entirely low. So this entire low in cost will actually demonstrate that our model has an improved accuracy. So actually we want to perform this kind of stuff. We are considering the global minima for the cost function. And in this case, our global minima is just achieved in the weight of say for example 3. So we have to obtain to this particular global minima. So in that case, we have to move our weight from 1 till 3 in some sort of automated manner. So this automated manner will come from the gradient descent algorithm. So this gradient descent algorithm will check upon the gradient at each of these functions. So in a simpler manner, the gradient is actually the derivative of a function at a particular point in this curve. So in this case, this is the gradient at this particular point of this entire curve such that the gradient is something positive. So in that case, if this is positive, we have to just minus this gradient such that it moves to the minimal point. So now I will just make a mathematical introduction of the gradient descent function. So in order to optimize the weights, the weight updation parameter is given as weight new is equal to weight old minus alpha is the learning rate. I will discuss about the learning rate in a few more minutes. And then here comes the partial derivative of dou by dou w of j of theta. So we are differentiating the cost function with respect to the weights such that we will get an updated weight, and this updated weight will be subtracted from the previous weight along with the multiplication of learning rate such that our new weight will be produced. So calculating the further of this, so we can leave all this and I will just calculate the differentiable part. So j of theta is given as 1 by 2 star n, summation I is equal to 1 till n. yi hat minus yi, the whole square. So this 2 will come this side. So since the derivative of x power n gives me n x power n minus 1, so I will automatically get 1 by n, and the only left part is summation of n, and then yi hat minus yi, and then this yi hat is can be explained as where m is the slope, x is the input feature, and c is the intercept. So this is a formula for the linear regression. Check on my previous video for this particular equation understanding. So differentiating this particular equation will just gives me xi as the differentiated one. So I can keep it here as xi. So this is my weight updation parameter. So like this ways, we can also calculate for the bias. With respect to bias, I will be differentiating the j of theta. So it is same as the previous above equation. For time purpose, I'm skipping the above steps, and we get yi hat minus yi, and here I get 1 as the differentiated output. Why? Because so in a linear regression equation, you can see here mi into xi plus c is the linear regression equation. So here we are just differentiating with respect to the bias, which is the c intercept. The coefficient along with c is actually 1. So after differentiating c, we are only left out with 1. So summing up, okay, I think you are all clear up to this. And then the learning rate part. So the learning rate actually, you can see here, the learning rate is actually multiplied with the gradients of the function. So we can just make a place of this multiplicative factor to improve the training period. For example, if our gradient initially lies here and our learning rate is actually a very minimal one, say for example 0.001. So this gradient into the 0.001 will actually make my gradient to jump to this part. Okay. So and our ultimate goal is to just descend this entire function and to initial and finally to reach this global minimum. So if we keep our learning rate as a very huge one, say for example 1.1, so from the gradient here, it actually make a huge leap to this particular curve, and then it just moves in a very randomized manner, and it would take some computational cost to reach the global minimum. So while choosing the learning rate, we have to be very careful with this, and it's also is a hyperparameter. So we can also test out with various set of hyperparameters, various set of values for this learning rate, and to choose an optimal one. So these are the gradient descent techniques. So up to this is the actual intuition of the gradient descent. So there are actually several variants of gradient descent. They are stochastic, batch, and mini batch. So stochastic is as actually for each data point in my data set, weight updation will happen for each data set. Say for example, so the error difference is 2, 2, 2, and then the gradient descent will be happening by the utilization of these two equations. My new weight will be updated for each data set in this particular stochastic gradient descent. And in the batch gradient descent, this entire 3 rows will be considered for the calculation of the gradient for just one updation. So in the stochastic gradient descent, each row will update the weight, but in the batch gradient descent, these 3 rows will be considered only for a single weight updation. So this is the batch gradient descent. And in the mini batch gradient descent, this particular 3 set of rows will be segregated into batches, and each batch is responsible for the weight updation of new weights. Say for example, I have 10 rows, and then I will be considering the 2 batches. So the first batch contains of 5 rows, and the second batch has 5 rows, and this 5 rows is responsible for a single weight updation, and the next 5 rows is responsible for a single weight updation. Now let's move into the demonstration via Python. So this is a simple linear regression implementation by utilizing the NumPy package. So I have linearly spaced my integers from 0 till 100 with 100 data points, and I have segregated the training data and testing data, and I have created a model function which accepts x and y as input, and my alpha is the learning rate, which is actually in this case 0.0001, and the epochs. Epochs is actually the iteration count, or else the total number of iterations required to train our model. So initially, I have made the weights and bias to zero point 0.1, and I have initialized the epoch, and then I have been utilizing the total loss to just demonstrate at the end of each epoch how much loss is just computed. Okay, so here you can see the output is nothing but m into x plus c, which is our actual linear regression equation. So and this loss is actually the error function. Error, we are just calculating the error function, which is nothing but output minus y of I, which is actually the actual output. So it is powered to. Okay. So and then we are calculating the gradient weight and bias with our gradient descent equations, which I have previously explained, which is the 2 into output minus y of I into xi for weight and into 1 for bias. And then I have been updating my weights for each input data, which is x of I. You can see here the weight, I have been subtracting the new weight with the whole weight. The loss is just printed for each part. So when I run this, okay, so you can see here the prediction actually resulted in the loss in a minimal manner. For example, so you can see here our testing data has 180 as the input, and my y test has actually 180. So the difference you can see here is actually 0.08. Okay, so this is actually the stochastic gradient descent, and I have also implemented the batch gradient as well as the mini batch gradient descent. So you can view my GitHub, just go through all of these codes, and I will catch you up with my next video. Thank you.